one more thing that we wanted to talk about buffered solutions is an easier way for us to do some calculations. So remember that a buffer will prohibit the pH from changing very drastically when you add more acid or base to a buffered solution. And we talked about all of this in section 8.8. So we also kind of talked about in 8.7 how the pH is related to pKa when you have a weak acid, and when they are equal and what that is helpful for. Okay, so now we're going to talk about a little bit more with that relationship. So it is related to the pKa when we have the concentration of the conjugate acid-base pairs involved. And this is a consequence of the equilibrium expression that is associated with the dissociation of a weak acid. So when we have our weak acid react with water, and then the other products in the equilibrium expression would be the hydronium ion, or H+, and the conjugate base. Okay, so we ended 8.8 with that. So the Henderson-Hasselbalch equation describes this relationship and uses the ratio of the conjugate base concentration to the acid concentration as a correction or an addition to the pKa in order for you to find the pH value. So just notice what goes on top in that log function. Okay, so when we use this relationship, adding small amounts of acid or base to the buffered solution will not significantly change the ratio of the concentrations. So because of this, there is not a significant change to the solution's pH, which would then mean that when you do change the pH because of the addition of an acid or base, it's going to be a lot less than it would be when there is an absence of the buffer or just plain water, right? So again, there's not very much change like we saw in example 17 of section 8.8. Okay, so I have example 18 here for us to see how to use this equation to help us with that. So we want to calculate the pH value of a solution that contains 0.75 molar lactic acid. Lactic acid is the acid that builds up in your muscles, which makes you sore. You guys know what that is, right? Hopefully. And so it has a solution of that with 0.25 molar sodium lactate. So we are going to just use this information to plug in and solve for this pH very simply. Okay, so the pH is equal to the pKa plus the log of the conjugate base concentration over the acid concentration. So P in front of a number or a letter, remember, is negative log. We are supposed to associate that. So when we see pH, we know it's the negative log of the H+. When it's pKa, that means it's negative log of the Ka. So we're going to take the negative log of our Ka value that's given, 1.4 times 10 to the negative 4, plus the log of, and then this is where the concentrations come in. So the lactate, the sodium lactate would be the conjugate base, is that lactate part. So we'll put 0.25 on top over the acid concentration of 0.75. Okay, so then just make sure that you type it in your calculator properly, and you should get that the pH is 3.38. Okay, now you could solve this problem the long way, like we did in 8.3, 8.7, those kind of things, where we figure out the ice chart and then we plug into the equilibrium expression and solve for the hydronium concentration and do all that work. But this is just a little bit simpler way to help us solve for pH values.